Imagine for a moment standing at the very edge of everything. Not the edge of a room or a country or even a planet, but the edge of time itself, billions upon billions of years from now, watching the last star in the cosmos flicker and go dark. It sounds like science fiction. It sounds like the kind of thing that belongs in a horror film, not a physics lecture. But here is the strange and beautiful truth. The end of the universe is not a myth, not a metaphor, not a piece of poetic speculation. It is a prediction written into the very equations that also tell us how a clock ticks slower near a black hole, how a beam of light bends around the sun, and how two particles separated by the width of the galaxy can still, in some ghostly way, be connected. Tonight, we are going to walk that path together. We're going to start with something you think you understand perfectly well, something you experience every single second of your life. And by the end, I promise you, it will feel like the strangest, most alien thing you've ever encountered. That something is time. Most of us walk through life assuming time is a kind of universal river, flowing at the same rate for everyone, everywhere, carrying us all forward together from birth to death, from breakfast to bedtime, from the Big Bang to whatever waits at the end. It feels obvious. It feels like common sense. And yet one of the deepest lessons of modern physics is that common sense is a spectacularly unreliable guide to reality. In the early years of the 20th century, a young patent clerk in Switzerland, a man who had been rejected from academic positions, a man whose own professors thought him unremarkable, sat down and asked a question so simple a child could pose it, yet so profound it would topple centuries of assumption. What would happen, he wondered, if you could run alongside a beam of light? Albert Einstein's answer to that question didn't just refine our understanding of light. It shattered our understanding of time and space themselves and fused them into a single entity physicists now call space-time. Here's the core of it, and I want you to really sit with this because it is one of the strangest facts you will ever learn. The speed of light, roughly 670 million miles per hour, is not just fast, it is fixed. It is the same for every observer in the universe, no matter how fast they themselves are moving. Think about how bizarre that is. If you're standing on a train platform and a train roars past at 60 miles an hour and someone throws a ball forward from the train at 10 miles an hour, you would measure that ball moving at 70 miles an hour. Velocities add, that's ordinary experience, that's common sense, that's Newtonian physics, and it works beautifully for trains and balls and everyday objects. But light refuses to play by those rules. If that same person on the train shines a flashlight forward, you don't measure the speed of light plus the speed of the train. You measure exactly the same speed of light as if you were standing perfectly still. Nature had to break something to keep that constant. And what nature broke, what Einstein discovered it broke, was the flow of time itself. If the speed of light must remain fixed for everyone, then something else has to give. And that something is our intuitive sense that time ticks at the same universal rate no matter who is measuring it. Einstein showed that a clock moving relative to you runs slower than your own clock. Not because the mechanism is faulty, not because gravity is tugging at the gears, but because time itself, the very fabric through which that clock ticks, flows differently depending on your motion through space. This isn't some exotic effect confined to particle accelerators and thought experiments. It is measured, verified, confirmed thousands of times over. The GPS satellites orbiting our planet right now have to correct for this effect using Einstein's equations because their clocks, moving relative to us and sitting in a weaker gravitational field, tick at a very slightly different rate than clocks here on the surface. Without that correction, your GPS would drift off by miles within a single day. We are, in a very real sense, using Einstein's revision of time every single time we use a map app on our phones. But Einstein wasn't finished. A decade after his special theory of relativity, after years of what he himself called the most exhausting and exhilarating work of his life, he unveiled something even more radical, general relativity, a theory of gravity unlike anything that came before. Isaac Newton had described gravity as a force, a kind of invisible rope reaching out from the sun and yanking the Earth into its orbit. It worked, mathematically, astonishingly well for over 200 years. But Einstein saw something Newton couldn't. He realized that gravity isn't a force reaching across empty space at all. It's the shape of space and time themselves. Picture a stretched rubber sheet and imagine placing a heavy bowling ball at its center. The sheet curves, it dips, it warps around that mass. Now roll a marble nearby, and instead of moving in a straight line, it curves inward, spiraling toward the bowling ball, not because something is pulling it, but because it's simply following the curved shape of the sheet beneath it. That, in essence, is Einstein's vision of gravity. The sun doesn't reach out and grab the Earth. The sun warps the fabric of space-time around it, and the Earth, in its orbit, is simply following the straightest possible path through that curved landscape. This picture, strange as it sounds, has been tested again and again, and it has passed every single time. In 1919, astronomers traveled to observe a total solar eclipse and watch starlight bend as it passed near the sun's mass. Exactly as Einstein's equations predicted, deflected not because light has any mass to speak of, but because the very space that light travels through was curved by the sun. That observation made Einstein a global celebrity overnight, and the predictions kept coming. Black holes, regions where space-time curves so extremely that not even light can escape, were once considered a mathematical curiosity, an oddity that surely couldn't exist in the real universe. Today, we have photographed them directly. Gravitational waves, ripples in the fabric of space-time itself caused by cataclysmic collisions between black holes billions of light years away, were predicted by Einstein in 1916 and finally detected exactly 100 years later in 2015, causing a shudder in the machinery of our detectors so infinitesimally small it was like measuring a change in distance to the nearest star thinner than the width of a human hair. Space and time are not a passive backdrop against which the events of the universe unfold. They are dynamic, flexible, participatory. They bend, they stretch, they ripple, and they can, under the right conditions, even come to an end. Which brings us naturally to the beginning, because to understand how the universe might end, we first need to understand how it began. If you run the equations of general relativity backward, tracing the expansion of the universe in reverse, you find that everything we can see, every galaxy, every star, every planet, every atom in your body, was once compressed into an unimaginably hot, dense state smaller than a single atom, all of existence packed into what physicists sometimes uncomfortably call a singularity. About 13.8 billion years ago, that state began to expand, and it hasn't stopped expanding since. This is the Big Bang, and I want to correct a common misconception right away, because even the name is a little bit misleading. The Big Bang was not an explosion happening at some particular point in an already existing empty space, the way a firework explodes in the sky. It was the expansion of space itself, everywhere, all at once. There was no center to the Big Bang the way there's a center to a firework. Every point in the universe was, at that moment, the center, because every point in the universe was, in some sense, everywhere. For the briefest of instants, the universe underwent something even the Big Bang model alone struggles to explain, a period called cosmic inflation, in which space expanded at a rate far faster than the speed of light itself, a fraction of a second, in which the universe ballooned in size by a factor so large it's almost meaningless to write down the number. This isn't a violation of Einstein's speed limit, by the way. That limit applies to things moving through space. Space itself, the fabric, the container, is under no such constraint. It can stretch as fast as it wants, and as the universe cooled from that unimaginable initial heat, particles condensed out of pure energy, quarks bound together into protons and neutrons. Protons and neutrons eventually captured electrons to form the first atoms, hydrogen and helium, and gravity, patient and relentless, began pulling those atoms together into clouds, and those clouds collapsed into the first stars, and those stars forged in their nuclear furnaces every heavier element in the periodic table, the carbon in your cells, the calcium in your bones, the iron in your blood. We are, quite literally, made of stardust, the ash of long-dead stars, reassembled by the patient hand of gravity and chemistry into something that can look up at the night sky and wonder about its own origins. Now, here is where the story gets even stranger, because for decades, physicists have been trying to reconcile Einstein's beautiful theory of gravity, which describes the large-scale structure of the universe with breathtaking precision, with quantum mechanics the equally successful but wildly different theory that governs the behavior of particles at the smallest scales. These two pillars of modern physics are frankly at war with each other. General relativity describes a smooth, continuous fabric of space-time. Quantum mechanics describes a universe of probability, uncertainty, and jittery, unpredictable fluctuations, even in what we think of as empty space. Zoom in closely enough to scales almost inconceivably small. And quantum mechanics tells us that space-time itself should become a seething, foaming, chaotic mess, nothing like the smooth, curved sheet of Einstein's vision. Reconciling these two descriptions of reality is without exaggeration one of the greatest unsolved problems in all of science, and it's here that string theory enters our story. String theory proposes something audacious. It suggests that the fundamental constituents of reality are not point particles, the way we've traditionally imagined electrons and quarks, dimensionless dots with no internal structure. Instead, string theory proposes that at the very smallest scales, far smaller than anything we could ever hope to observe directly with current technology, matter is made of tiny vibrating strands of energy, or loops, vibrating in different patterns. And here is the elegant idea at the heart of it all. Just as a violin string can vibrate in different ways to produce different musical notes, these fundamental strings can vibrate in different patterns to produce what we perceive as different particles. An electron isn't a separate kind of thing from a quark or a photon. They might all be the very same kind of string, simply vibrating differently, playing different notes in what some physicists have poetically called the cosmic symphony. It's a thrilling idea because it offers, at least mathematically, a way to unify gravity with the other forces of nature within a single, elegant framework. But string theory comes with a strange price of admission. For the mathematics to work out consistently, without contradictions, without impossible infinities breaking the equations, the theory requires more than the 3 dimensions of space we experience every day. Depending on the version of the theory, string theory calls for 9, 10, or even 11 dimensions of space and time. Now, before you dismiss this as pure fantasy, consider that this isn't the first time physics has demanded we expand our notion of dimensions. Space and time themselves, once thought of as entirely separate things, one absolute, one universal, turned out through Einstein's work to be 2 aspects of a single 4-dimensional fabric. String theory simply pushes that idea further, suggesting there may be additional dimensions curled up, compactified, hidden at scales so unimaginably tiny that we simply cannot perceive them in daily life. The way an ant walking along a garden hose might only perceive the single dimension running along its length, unaware of the tiny circular dimension wrapping around its circumference. It's a beautiful, seductive idea. I'll be honest with you, it remains unproven. No experiment has yet confirmed the existence of these extra dimensions or the strings themselves, and there are brilliant physicists who question whether string theory will ever be testable at all. But even in its unproven state, it has forced us to ask deeper questions about the nature of reality than almost any other framework in the history of science, and that in itself has value beyond measure. Let's step back now and ask a question that naturally follows from everything we've discussed. A question that has haunted humanity since we first looked up at the night sky and wondered what those distant points of light might be. Are we alone? The observable universe contains something on the order of 2 trillion galaxies, each containing on average hundreds of billions of stars, and we now know, thanks to decades of exoplanet discoveries, that most of those stars host planets of their own. The numbers involved are so staggeringly large that it seems almost arrogant, almost a failure of imagination, to assume that Earth is the only place where the particular chemistry of life managed to ignite. And yet when we scan the skies with our most sensitive instruments, when we listen for radio signals, when we search for the telltale signatures of technology on distant worlds, we hear nothing. Silence. This contradiction, the overwhelming statistical likelihood of life elsewhere set against the deafening silence we actually observe, is known as the Fermi paradox, and it remains one of the most tantalizing open questions in all of science. There are many proposed resolutions. Perhaps life is common, but intelligence is exceedingly rare. a fluke of evolutionary history that might have happened only once in the observable universe. Perhaps intelligent civilizations tend to be short-lived, destroying themselves through war, environmental collapse, or unforeseen technological catastrophe before they ever develop the ability to signal across interstellar distances. Perhaps they are simply too far away, separated not just by staggering distances of space, but also by staggering gulfs of time. Civilizations rising and falling like sparks in the darkness, never overlapping long enough to ever say hello. Or perhaps, and this is the possibility that keeps me up at night in the best possible way, we simply haven't been looking the right way, listening for the right signals, imagining intelligence in the right form. Our search has largely assumed that alien civilizations would communicate the way we do, with radio waves, with recognizable patterns. But what if intelligence out there is so different from our own that we wouldn't even recognize its signature if it were staring us in the face? What if it doesn't inhabit stars and planets the way we do at all? These are humbling questions, and I think that humility is exactly the right posture to hold when confronting the scale of the cosmos. And this brings us at last back to where we began, to the end of everything. Because understanding how the universe started and how it's structured allows physicists to make genuine, mathematically grounded predictions about how it will end. And I have to tell you, the picture that emerges is one of the most sobering, awe-inspiring things in all of science. In the late 1990s, astronomers made a discovery that shocked the entire field. By observing distant supernovae, stellar explosions so bright they can be seen across billions of light years, and comparing their brightness to their redshift, astronomers expected to find that the universe's expansion was slowing down over time, the natural consequence of gravity pulling everything back together. Instead, they found the opposite. The expansion of the universe is accelerating. Galaxies aren't just moving apart from us, they're moving apart faster and faster as time goes on, pushed by a mysterious, repulsive influence physicists have named, with a certain resigned honesty about how little we actually understand it, dark energy. We don't know what dark energy fundamentally is. We know how it behaves, we can measure its effects with remarkable precision, but at a deeper level, its true nature remains one of the greatest mysteries in modern physics. If dark energy continues to behave the way our best current measurements suggest, the ultimate fate of our universe is a scenario physicists call the heat death, or sometimes, more evocatively, the big freeze. Here's how it unfolds on a time scale so vast that human history, indeed the entire age of the universe up to this point, is a single tick of the clock by comparison. As the expansion continues to accelerate, galaxies beyond our local cluster will eventually recede faster than the speed of light can carry their light back to us. They won't be destroyed, they'll simply vanish from view forever, redshifted into invisibility, causally disconnected from us for all time. Trillions of years from now, the stars themselves will begin to run out of the hydrogen fuel that powers them. Star formation will slowly grind to a halt as the raw material for new stars becomes exhausted and diluted across the ever-expanding cosmos. One by one, the lights will go out. The last, faintest red dwarf stars, the most fuel-efficient and long-lived of all stellar types, will flicker for trillions of years before finally fading into cold, dark stellar remnants. Even after every star has died, the story isn't quite finished, because on truly staggering timescales that make trillions of years look like an eye blink, even matter itself may not be permanent. Some theories in particle physics suggest that protons, the very building blocks of atomic nuclei, may eventually decay, breaking down into lighter particles over a time scale so long it dwarfs comprehension, a number followed by so many zeros that writing it out would be an act of futility. If this is true, then eventually even the cold, dark remnants of stars, the black holes, the dead planets, the frozen husks of what were once galaxies, will simply dissolve atom by atom into a thin, diffuse mist of subatomic particles. And even black holes, those ultimate graveyards of matter, are not eternal. Stephen Hawking showed in one of the most profound results in modern theoretical physics that black holes slowly radiate away their mass and energy in the form of what we now call Hawking radiation. evaporating over unimaginable eons until nothing remains but the faintest whisper of energy, dispersed so thinly across the vast reaches of an ever-expanding universe that it can barely be called anything at all. The end result, the ultimate fate suggested by our current best understanding of physics, is a universe stretched to an almost infinite size, its temperature approaching absolute zero, its matter diluted so thinly that meaningful interactions between particles become essentially impossible, a state of maximum entropy, maximum disorder, where nothing changes because there is no longer enough structure, no longer enough energy gradient, no longer enough difference between one point and another to make change possible. No stars, no light, no chemistry, no thought. Just an endless, silent, freezing darkness stretching on forever. It is, I'll admit, a haunting picture, but I want to leave you with something other than dread, because I think dread misses the point entirely. This isn't a story about an ending we should fear. It's a story about scale, about our place within an almost inconceivably vast unfolding of space and time, and about the extraordinary improbability of what's happening right here, right now, in this brief cosmic moment when stars still burn, when chemistry still happens, when creatures like us can arise from stardust and turn our attention outward and inward at once, asking questions about beginnings and endings that the universe itself, as far as we know, has never asked about itself before we came along to ask them. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible at all. That creatures made of the same atoms as stars and rocks and empty space could develop minds capable of deriving the equations that describe the birth and death of everything. Minds capable of calculating, from the safety of a small blue planet orbiting an ordinary yellow star, the ultimate fate of 100 trillion galaxies. That, to me, is the real wonder here. Not that the universe will end in cold and silence unfathomably far in the future, but that for this fleeting sliver of cosmic time, matter organized itself into beings capable of understanding, even partially, even provisionally, the grand sweep of space and time, from the first fraction of a second after the Big Bang to the final faint whisper of the last evaporating black hole. We are, each of us, a temporary arrangement of stardust that learned to ask where it came from and where it's going. And in the act of asking, in the act of building telescopes and writing equations and reaching for understanding, we give this brief, bright moment in the life of the universe a kind of meaning it would never have on its own. So the next time you look up at the night sky, remember that you're not just looking at ancient light from distant stars. You're looking at the raw material of your own body, and you're looking, however dimly, toward an ending that lies so far in the future it can barely be called a part of the same story as us at all. And yet somehow, impossibly, wonderfully, it is.